I'm going to generate an AR1 series, and we've done it before with AR2. The C is 1024. Length of the series 256. Let's see. You can give me a value for the coefficient.
0.47.
0.47. Okay. And I'll make it 0.48. I like ours too. Still right.
Let's say that next is yours.
Okay, so that is going to generate an AR1 series. And last time I showed you how to get the autocorrelation function. In R, you can get it directly using PACF. I'm going to save it to a variable because we need to look at the values, the exact values. So by default, it is going to plot the ACF. But if you want the exact values, you can save it to a variable. Okay. And this, I deleted it. It's still missing. And I see. It's not happy here because it is giving me an error. Down here it says arg should be correlation, covariance, partial. Good. So we know the correlation part. So by the looks of it, is it stationary? Does it look like it is stationary? When in doubt, mean 0, we don't have a mean. So outline. There it is. And you can see it seems like the observations are evenly spread out about the central mean level, which is 0 in this case. And that is the autocorrelation function. Seems like you have row 0, which is 1, as expected. You're correlating the series to itself. Off by 1 lap, and lap 2, lap 3, it just goes away. So, as far as an AR1 model is concerned, you can use PACF. Let's see what the row values are. In the original model, the true value of the coefficient that I used in the simulation is 648. And if you look at our derivation said row 1 is equal to psi 1, the coefficient. So if you find an estimate for row 1 using the series, you can fit them all, correct? Okay, let's see what row is. I decided to make Joe happy. 0.466. Thank you. So row 1 ended up being 0.466. You can round it to 0.47. So using PACF, the estimate for psi 1 is and it is doing a good job. Do you agree? Yes. Now, what would happen if I don't observe it for a length of 256?
Are you saying, well, if you observed it significantly less, or significantly more?
Less. Good question. Let's say I pick a number less than 50.
47.
47, okay. So 47. That's what I get. Sure, it is dampening back and forth. It tells me it is an AR1. But let's look at the estimate. I end up getting 0.43. It is off, way off from 0.48. Fundamental principle of statistics, bigger the sample, better the estimate. So we're going to lose accuracy if we don't observe a series enough, which makes perfect sense. If you want to know a trend, you've got to make sure that you have observed a particular series over a long period of time. Agreed? So in this case, 0.423 is off from 0.48 because I'm using a small sample size. So if you Google and look at most time series data, they are pretty lengthy. They would have 200 data points, 300 data points, etc. So with an AR1 model, you can simply use the ACF plot and get an estimate. However, what's a note? There is a thing called PACF, stands for partial autocorrelation function. I'll call it very easy. Couple of ways in which you can get partial or autocorrelation function. One, you can take the ACF function and put another argument that says partial, or use the function PACF in R. Put Y, colorful, and let's see what happens. I've saved ACF to row, and I've saved PACF to drop R hop. So got two different variables, pixels. ACF. Point 466. R hop is PACF. Where do you see 0.466? It is the very first element, unlike ACF. With ACF, the first element is 1, because it is the autocorrelation. In partial autocorrelation, it is not. 1, it actually gives you the exact 0.466. So, any thoughts as to what a partial autocorrelation is? You won't see it with an AR1 case. It would make better sense with AR2. Partial autocorrelation is a case where, let's say you have time point t, you directly correlate it with time point t minus 2 by excluding whatever that's in the middle. So you're making a direct connection. But if it's autocorrelation, xt minus 1, then xt minus 2. With an AR1, it doesn't matter because xt minus 1, and if you're going to go for partial autocorrelation, is there something between xt and xt minus 1? No, it's nothingness, so it doesn't matter, which is why we are going to get the exact value. It doesn't matter whether you use ACF or PACF with AR1. Joe, question?
So, just so I think about this right, when you're using a PACF, you're correlating xt with essentially xt minus 2.
Yes, or xt minus 3. You know, condition. The proper word is conditioning. You know, with whatever values you have in the middle. But in simple terms, you are pretty much not observing whatever that's in the middle. So xt, jump all the way, let's say xt minus 8, hypothetically. AR8 model. We won't go that far in real life, but hypothetically. So HCF is going to start at xt, take into account of xt minus 1, 2, 3, 4, 5, 6, 7, and 8. So it is in a recursive manner, it is going to take all those values into account. But PACF, on the other hand, will have xt and go directly to xt minus 8, assuming everything else in the middle is done. Right? And if I ask you, okay, I want to know how xt is correlated with xt minus 8, which is going to be easy. It's PACF, right? And PACF only matters with AR models, not with MA models. Good. And again, doesn't make any sense, or doesn't make good sense to use PACF for an AR1 model because there's nothing in between time index t and time index t minus 1. So PACF becomes useful when we go to higher order AR models. Good. Any questions?